Okay, good afternoon. Thank you for the introduction. I hope everybody enjoyed their relaxing lunch. Now we're going to continue with the EMI session. So my topic today will be on a PCB inductor with integrated shielding to contain the electric field and reduce the common mode noise. So I'll start by talking about problems of parasitic couplings for high frequency, high density power converters. And specifically, we're going to identify one capacitive coupling between our power stage and our EMI filter that can actually significantly increase our conducted EMI emissions. Then we're going to propose a PCB inductor structure that has integrated shielding within the PCB in order to minimize this capacitive coupling and reduce our noise emissions. And finally, we'll show the experimental results as well as the summary and conclusion. So we can start by taking a look at a traditional silicon-based server power supply. So due to the large switching energy or switching loss of the silicon MOSFET device, we're restricted to use relatively low switching frequencies. So as a result, we have to use bulky Litz wire magnetics. Because of these low switching frequencies, we need more turns on our magnetic components, so we have to use these Litz wire components that you see here. The issue with this is the Litz wire magnetic components, relatively large, they have a labor-intensive manufacturing process as well because we cannot integrate these using PCB windings or something like this. Also, because these are typically hand wound, there's going to have a larger tolerance in terms of the manufacturing consistency. And finally, because of the relatively low switching frequency, we have to use a bulky two-stage EMI filter. So let's take a look at the comparison of the silicon device compared to the gallium nitride device. So this is from a prior CPES work, and basically, as we know, the turn on and turn off energy will be lower for the wide bandgap device, and in this case, we see a reduction in both. However, if we take advantage of the critical conduction mode, zero voltage switching, we can, of course, eliminate our turn-on loss. So in this case, if we just compare the turn-off loss, we see actually 10 to 20 times lower loss. So by using the ZVS with the gallium nitride wide bandgap device, we can actually have 10 to 20 times less total switching loss. And to take advantage of this, we can actually increase the switching frequency of our converters significantly. So this is from the prior CPES work. We can actually use 1 to 2 megahertz as our switching frequency for our PFC stage and our resonant DC-DC stage. By using this high switching frequency, we can still achieve a very high efficiency, but we can also take advantage of PCB magnetics because there's fewer turns now. And with the PCB magnetics, we have a couple advantages. The first is we can have automated manufacturing as these are integrated within our circuit board. And this gives us a very good tolerance or control for the design of our windings. And with this very tight tolerance, we're able to actually use some advanced EMI mitigation techniques. For instance, on the PFC stage, we can use these balanced coupled inductors to reduce our common mode noise. And also on our resonant DC-DC stage, if you remember from Dr. Qiang's tutorial, we can also use shielding between our primary and secondary windings within our PCB transformer. So both of these techniques can allow us to reduce our EMI and then use a small single-stage filter. However, we do need to be mindful of the effects of capacitive and inductive couplings within our power converter. So especially as we adopt these wide bandgap power devices and we take advantage of the higher switching frequency, also faster switching speeds, of course this is going to increase the dVdt and dIdt of these power signals. At the same time, as we take advantage of the high switching frequency, we also have a more compact converter layout with smaller passive components. However, as we push different areas of the converter very close together, of course this will tend to increase the capacitive and inductive couplings between these different areas due to their proximity. So we need to be aware that these parasitic couplings within our converter hardware may introduce additional paths for our EMI noise. So let's just take a look at the conducted EMI. If you're not familiar, we use a line impedance stabilization network between our power source and the converter under test, and this allows us to measure our noise. So in this case, we just have a synchronous buck converter, and we're going to measure the noise. So we have these listens here between our DC source and our converter. And so we can analyze two different modes of our conducted noise. The first is the differential mode noise, which flows between the two input power lines. So this is mainly associated with the current ripple of our input power. The other hand, we have the common mode noise. So this is the noise which is common to both power lines, and it returns through the earth ground. So the way this returns is there's always going to be some parasitic capacitance from the switching node of our circuit to the earth ground or the chassis, and this is what creates the path for the common mode displacement current to couple to the earth ground and then return through your listens. So we're going to focus on this common mode noise for this presentation. So from our CM noise path that we identified, we can actually develop a simple CM noise model. We're just going to get rid of a lot of this structure of our listens, as they're not very important for EMI standpoint. We're just going to keep these two 50 ohm EMI measurement impedances. The second thing we're going to do is replace the half bridge of our PWM converter with a single voltage source. So in the case of the CM noise, actually it's the switching voltage which creates our noise. So we can neglect the input current and just replace this half bridge, and all the nonlinearities of the gate drive, the actual switching devices, we can just measure this or simulate the switching voltage, and this will be our noise source. So we can actually look at the conducted CM noise emissions of this converter. We'll start with no EMI filter as a baseline, and based on the operating condition of this converter, we're going to have a switching voltage waveform that we talked about. So this is just the voltage across the synchronous rectifier for this buck converter, and we can see we're switching 400 volts at 500 kilohertz for this demonstration. And this is more useful for us in the frequency domain for the EMI. So here we can see our fundamental component at the switching frequency of 500 kilohertz. Now, due to this capacitive coupling that we talked about between the switching area and the earth ground, this switching voltage creates this common mode current, and this is the source of our common mode noise. So now, of course, we'd like to reduce the CM noise to meet some standard or regulation. So to do so, we're going to add an EMI filter for our power stage. And here we're just going to try a single stage filter. However, after we add this filter, we find there's only about 10 dB reduction in the CM noise. So this is not a very successful reduction in our noise. So maybe we just need to use a larger EMI filter. Maybe that's the issue. So here, instead of a single stage filter, we instead try a larger two-stage EMI filter. However, even with this one, we still see a pretty marginal reduction in the CM noise. So maybe it's only another 1 or 2 dB compared to the single stage filter. So there's something else going on here. It's not just the filter design. And in fact, we need to consider these near-field couplings that I mentioned earlier. So specifically, there's two areas of our circuit. The first is the switching voltage area, which includes the two gallium nitride switches, which are under this heatsink, and this PCB inductor. The second area is this input side of our EMI filter. So this is the side of the filter which connects to our input power supply. And because there's going to be some distributed parasitic capacitance between these two regions of our circuit, we're always going to have some EMI noise capacitively coupling from this area to this area. And this is actually the cause of our CM noise. So we can see the noise path here. Once the CM noise flows through this coupling, it faces only a low impedance return because we only have these 50 ohm listen impedances and then the low impedance of our Y caps. So somehow, instead of our filter attenuating the noise, when we have this coupling, our filter has no effect on the noise. It's actually not attenuated at all because it's only a low impedance return. So to actually reduce our noise further, it's not about the filter design anymore. We have to do something about this coupling. So there's three options to reduce this coupling. One would just be to move these two areas further apart. However, this is obviously not very practical, usually, because we're going to have to increase the size of our layout. So that's going to affect our power density. So the second option would be to reduce the physical size of these circuit areas. So we have to use smaller components or smaller traces. And obviously, this is not very practical either, as we're going to have to change our converter design. So finally, the preferred option is going to be to use some type of electrostatic shielding to screen or shield this capacitive coupling. So we can either shield this area, put a shield between them, or shield both. So let's look at how we can use shielding for this. So first option would be to shield the EMI filter. And this is an effective approach if you'd like to use this. However, the downside is we can't really integrate shielding within our automated PCB manufacturing process. Obviously, we have pretty large through-hole components for our EMI filter, such as the common mode choke and the film capacitor. So these are pretty bulky and hard to shield, unless we just design a full enclosure. So actually, we can instead put shielding around our switching area. And this will actually allow us to contain all these electric switching noise and prevent it from escaping to other regions of our circuit. And because of this wide bandgap based converter with the integrated PCB magnetics, we actually have a good opportunity to integrate shielding around this whole switching voltage area. So we can take a closer look. Here I just removed the heatsink from these devices and removed this ferrite core so we can get a closer look at the conductors. And to shield these power switches, in this case it's very convenient. We're already using topside surface mount devices, so we can just use our heatsink and tie the potential of this heatsink to some DC potential, and this will act as a shield for our devices. And then we also already have a ground plane underneath our devices on this PCB, so this will also help with the shielding. And now we're going to focus on how we can actually integrate shielding within the inductor. So even if you shield your switching devices, the inductor windings also carry the switching voltage, so they're going to make their own noise emissions unless you also put some shielding around the inductor. So let's look at how to incorporate shielding for the PCB inductor. So let's start with the original inductor design with no shielding. So we just have 6 turns on 6 layers. So here we have 1 winding per layer. And then it's kind of similar to how we use shielding for the PCB transformer between the primary and secondary windings. In this case, we're just going to put the shielding on the outside, and it's to shield the windings from the filter. So here we just add a shield layer on the top and bottom, and these do not carry the inductor current. They're just going to be held at a DC potential. So we can take a topside view. So this is the cross-sectional view of our windings. We can take a top view of our inductor. So here's the inner winding layers. So this is our switching node, and our inductor current flows around our center post. We use vias to drop to the next winding layer, and so forth. And after the 6 turns, our inductor current exits at our DC output voltage, because this is a buck converter. However, we can add our shield layers, and these will go on the top and bottom. They'll be identical. And here we just have another winding layer, except there's a cut to prevent creating a completed loop, which would cancel our inductance. And also, we're going to use a via just to connect both of these shield layers to the DC potential at the output of our inductor. If this is a boost topology, you would just do the opposite. So you would tie the shield layers to the input terminal, which would only be at line frequency. So the main thing is we don't tie the shield to the switching node. So in this way, we can hold the entire shield conductor at a quiet potential. Now we can take a look at the electric field from the PCB inductor windings. So with no shielding, it acts sort of like a point charge and creates electric field kind of in all directions. After we add these shield layers on the top and bottom, we can reduce our electric field. However, we're still going to have fields escaping laterally through the PCB dielectric. So we're going to also need to put some shielding on the side of these windings in order to shield this lateral electric flux. So here's a design we came up with previously where we can actually use conductive edge plating on the sides of our windings. So we had these cutouts in our PCB for the magnetic core. We can just add conductive edge plating to connect the top and bottom shield layers, and in this way we can completely enclose the PCB windings, and it acts like a very effective electrostatic shield. However, we do need to be mindful of the copper loss, especially the eddy losses which will be induced in these shield layers. So we're going to use a FEA simulation to study this effect. So starting with the original inductor with no shielding, just from the inductor current, we're going to have some DC winding loss due to the DC resistance of the windings, and we're going to have some effective AC loss, which is due to eddy currents causing the skin and proximity effects. So we're going to normalize that to 1 watt loss for this converter operation. And then after we add shield layers on the top and bottom, our winding losses are not going to change because we're not going to affect the current distribution within our windings. These remain the same. However, we are going to have some additional loss due to the eddy currents induced in these shield layers. So there's going to be some magnetic fields incident on these shield layers, and that would create a little bit of extra loss. So in this case, maybe 10 or 15% extra copper loss due to these eddy currents. However, after we also add the conductive edge plating, and now we've created a complete enclosure for our windings. However, now we have a very large eddy current induced in our shield. And specifically, these edge plating happen to be very bad. I won't go into the mechanism here, but it has to do with the magnetic fields going laterally through the PCB windings. This created a very large loss. So we have excessive eddy currents induced in the edge plating. So we want to come up with an improved structure to shield the inductor windings without creating these huge copper losses. So to do so, we're just going to replace the edge plating with these shield rings. So instead of using the conductive edge plating on the faces of our windings, we're just going to put a narrow copper ring on the inside and outside of these windings on each layer. And that way we can still contain the electric field while minimizing the eddy losses in the shield. Also, we really want to minimize all the extra copper loss, so we can also take a look at our shield layers on the top and bottom. Right now, these are just these solid shield layers with a single cut to prevent a shorted loop. However, we can also minimize the eddy currents here by creating this pattern. So we can add these radial cuts in our copper layers just to create this pattern. So this will still act as an effective shield, but here we can just minimize some of these eddy currents. And this is just an illustration here. In the actual implementation, we'd like to make this pattern very fine because we can maximize our shielding effectiveness and minimize the eddy loss. So based on the capabilities of the PCB manufacturer for a given copper weight, you can design a minimum copper trace width and a minimum clearance, and that can be used to define the pattern for your shield layers. So finally, we're going to experimentally verify this approach. So here I've just created two identical converter PCBs. These are both just basic synchronous buck converters for 900 watts, and both have the same inductor, except this one has no shielding, and this one has this low-loss shielding structure that we've just presented. So first thing we're going to do is measure the switching electric field above the converter to see if the shielding is effective. And to do so, we can use a near-field electric field probe, and then we actually have a robotic arm you may have seen during the dialogue session, which we can use to automatically position this probe above different areas of the converter and map out our electric field intensity. So here I've just added an animation. So we just write a script to position this probe, and at each point we use the oscilloscope to collect the waveform, and then we can apply the FFT. So we're going to look at the switching frequency electric field component above our converter. So here's the image of our converter. Here I've just overlaid this switching electric field component, and we can see above the power stage inductor we have a fairly large electric field, so it's about 7,000 volts per meter, just for the fundamental component. However, after we use the shielding integrated in our PCB inductor, now we see the electric field is basically eliminated. It's still there, but it's just reduced at least by 30 dB, so it's a good reduction. And so in this case, we've actually been able to completely contain all of the switching electric field energy, which was previously just radiating around our converter, and now it's effectively contained. So now we're also going to look at the conducted common mode noise. So as you remember from the start of the presentation, because of this switching electric field from our power stage coupling to our EMI filter capacitively, we had this effect where we couldn't really reduce our common mode noise, no matter how we designed the filter. So in this case, we're able to use our original single-stage EMI filter, but now we can have almost a 30 dB reduction in the conducted CM noise emissions, just because we added shielding on this PCB inductor. So in this case, we need to change the filter design or the converter operation, and we get a good reduction or a good improvement for our EMC. And finally, we just want to make sure that we're not adding too much copper loss using our shielded inductor structure. So to do so, we've just measured the converter operating efficiency. So we ran the two converters, one with the original inductor, one with the shielded inductor, ran them at the same operating condition, same inductor current waveform, and same power and voltage, of course, and we find only a very small reduction in our efficiency. So in this case, we have about 1.2, 1.25 watts extra loss for this 900 watt, almost 1 kilowatt operation level. So obviously, you're always going to have some small amount of loss depending on how you design this inductor, but from a system level perspective, we can get a great benefit in our EMC for a very small price and our efficiency. So to summarize, we've seen that the switching noise from our power stage can couple capacitively to the EMI filter, especially if you have a high frequency or high-density converter design. We'd like to contain all this noisy switching electric field, and to do that, we can actually integrate shielding within the PCB inductor. So in this way, we can take advantage of the automated manufacturing process for the PCB winding magnetics in order to contain this high-frequency noise. And finally, we've just proposed this low-loss shielded PCB inductor structure using the shield rings and the patterned shield layers. And with this structure, we saw that we can effectively contain our electric field noise and significantly reduce our CM noise emissions. So that's all for my presentation. Thank you for your attention.
Great timing, 20 minutes even. So we have 5 minutes for question. Any question, please use the microphone on the left and right side.
Hi, very nice work. I have a question. Could you go to the E-field measurement results you have?
Sure.
So based on the circuit model and the theory, right? So the reason there is an E-field, especially near field coupling, is there is a pulsating voltage node.
Right.
But in this measurement, it seems like the whole inductor become a E-field source. Could you maybe explain why the whole inductor becomes the major
Sure.
source?
Yeah, thank you for the question. So the reason is also this is a little bit maybe confusing because I had to skip over a couple of details, but in this case, we already shielded the devices, the switches, using the heatsink. That's why we don't also see switching noise above the devices. So now we're only left with the inductor's electric field. So the reason is the inductor windings are connected to the switching node on one end and the DC terminal on the other end. So we assume there's a linear voltage gradient moving from the switching node to the DC node, or if it's a PFC, it would be a low frequency AC node. And so there's always going to be some switching voltage. So maybe on the last turn, it's a small component, but you still have some switching voltage. All the turns will have, some switching voltage, which means they have some switching charge, and that's what creates this electric field.
Okay.
Also, the ferrite core has a very large permittivity, so that also kind of enhances the electric field that radiates from the inductor windings.
So it seems like all you need is a conductive path for this electric field to propagate, right? So what if you just ground the core?
Yeah.
Would help.
Yeah, that's a good point. So you can also use the core as a ground, especially for higher frequency. The conductivity of the core is pretty high, so maybe 1 Siemens per meter. And this is already fairly effective, so especially if your core encloses your windings. So sometimes the windings go outside the core, and then that's not going to work. So this one maybe is a better option especially when you have windings outside the core. But obviously in some cases, maybe your core needs to be grounded for safety reasons or insulation. Then in this case, this could also be a good option. But from my experience, in this geometry, the core doesn't close the windings, so the reduction in the CM noise was maybe 20 dB, and with the shielded windings, it was 28 dB. So you can still get a good benefit. It just depends on the inductor.
Yeah. Thank you. Very nice one.
Thank you.
Jarosław Lonarski, Kamis. Thank you for your great presentation and for the tutorial as well, because I see it's like was everything here. I have one question about the shielding and the patterns. If you consider frequencies for the patterns like clearance and thickness of the shape, like the width of the shape.
Oh, have I considered this one?
Yeah.
Yes, we have considered this one. So right now, I didn't really talk about how to design the shielded inductor. I just showed the concepts, but that's been our follow-up work since we had this idea. So from our experience with the optimization, the smaller that you make these cuts between the copper, the less electric field can escape, so that improves your shielding performance. And then the smaller you make the copper segment, the less eddy current there is. So obviously, to minimize eddy currents, you want to make this pattern as small as possible, or as fine as possible. But also, as you know, when we use a thinner copper layer, a lower copper weight, we can also use thinner copper segments. So it's a little bit complicated here, but generally for these shield layers, you want to use very thin copper and then use very fine pattern. But these shield layers will also be used in the rest of your converter PCB to carry current, so maybe it shouldn't be too small.
But did you see the relation between like expected frequencies and the clearances and the width of each pattern?
Oh, the frequency response?
Yeah. No, a relation between how to design the patterns and the clearance between the pieces you have on this picture and expected frequencies.
Oh, I see what you're saying now. Yeah, we haven't done the frequency analysis. So far, all the simulations have been at 500 kilohertz. It's true, as the frequency goes up, eventually the shielding will no longer become effective. But that is probably only going to be a concern when the wavelength becomes very, very small. So once it's around the same dimension as our clearance. But in this case, we're below 30 megahertz, I mean, at least for the conducted noise. So the wavelength is already going to be in the meters. So that this is basically an electrostatic shield. So there is no frequency response. Eventually there will be a frequency response, but at least below 30 megahertz, there's no effect.
Okay, thank you. Because you know, a similar effect is in RF design. If you do VS or something, you just design the clearance between them based on frequency, and I see some similarity here. Thank you.
Okay, thank you.
One quick question about the parasitic capacitance. So you do the shielding in this way, and each layer you will create a small capacitance between each winding to the shielding. Will cause some high frequency oscillation? Have you observed anything like that?
Yeah, thank you for the question. That's a very good point. So depending on the your switching frequency as well as the dielectric thickness, yes, you can increase your parallel capacitance. So in this case, you can probably see that the parasitic capacitance will be increased because this shield layer is tied to the inductor's output terminal. And we have this first winding is connected to our switching node. So this capacitance between these two layers is basically directly parallel across your whole inductor. So actually, we just looked at this recently. What we can actually do to minimize this capacitance is just change the order of the windings. So instead, we can put the first and second windings, which have the highest switching voltage, further from the shield layers. So we can put those in the middle, and then as we go out, we can move to the lower potential windings. Also, I do have if I go all the way to the end of my backup slides, I do have the inductor current waveform with the shielding. So even with the shielding, in this case, it's 500 kilohertz. Our resonant frequency from the FEA simulation and from our measured impedance is about 8 or 9 megahertz. So it's almost, it's over 10 times. So we didn't have any issues. But if you have a very high switching frequency, you need to pay more attention to this. You might have to use a thicker dielectric.
Thank you. Okay, thanks for the questions. Due to the time limit, we need to move forward. And thanks, Taylor, for the